about YCQL, but before we dive into that too much further, we really need to talk a bit about YugabyteDB Managed and the product that we serve. This is how we deliver YugabyteDB as a managed service. So instead of having to think about how to provision your infrastructure and how to get your database deployed into the cloud, YugabyteDB Managed helps developers really focus on what's really intrinsic or important to their business and leave all that provisioning and infrastructure management for YugabyteDB to manage. So with this, I just wanted to show you with this, you can actually have the ability to deploy your service and use the infrastructure without having to worry about security and scalability and factors like that. So it's very interesting and unique with this ability. Next slide, please. So let's go ahead and talk about what the agenda is for today. So first and foremost, we'll give some context of what distributed SQL is. So yes, there you go. Welcome to DSS, the Distributed SQL Summit. So give a little context first and foremost about what distributed SQL actually is. Then of course, we'll dive into the YugabyteDB architecture and really give you some context in relation to Cassandra, YCQL, once again, which is YugabyteDB's Cloud Query Language, and really shows you what the compatibility layer is with Cassandra's query language. And then of course, we'll dive even deeper about what makes YCQL unique, and that is with our semi-relational data modeling. And then we'll dive a little bit deeper into how secondary indexes really improve your query performance, as well as talk a little bit about data expiration. Next slide, please. Next slide, please. Thank you. So let's give some context. What exactly is YugabyteDB? So YugabyteDB is a geo-distributed database for modern enterprise to use as a system of record. So it's 100% open source. It's geo-distributed. So YugabyteDB supports online transaction processing for mission-critical applications. YugabyteDB is compatible with both PostgreSQL as well as the Cassandra APIs. So today, of course, we're going to talk a lot more about the Cassandra compatibility. We do have a course on Postgres. If you're interested, please go ahead and take a look at the university for that one. We actually have that course a little bit later today at DSS as well. So in order to understand YCQL, it's important to get some context of what Cassandra is and the advantages of having a semi-relational database. So Cassandra is a NoSQL database. It's really grown in popularity because of a few major features. And these features include the ability to handle web scale workloads due to its unique database structure. So Cassandra is actually very highly available as well. Very important for mission critical workloads because it has a distributed storage layer, just like YCQL. Okay, so however, Cassandra sacrificed a few things in order to get that distributed layer, including data integrity as well as ACID compliance to achieve that linear scalability to have performance at web scale. Excuse me. But the thing is, YugabyteDB was able to achieve that data integrity and the ACID compliance without having to give up and still retain that strong replication. Okay, so then, okay, next slide, please. So let's talk a little bit about what is distributed SQL. I think it's quite important, especially at a summit like this, to really get some context around what distributed SQL actually is, since you will hear that quite a few times today. So real quick, what is distributed SQL? You need 5 specific characteristics in order to be considered distributed SQL. Number 1, you need a SQL API. That seems pretty self-evident. You need a distributed data storage layer. Then, of course, you need to be able to replicate the data, not only just distribute it, but replicate it in order to get that resilience and high availability. Then, of course, we need to have a distributed query execution. And like I said before, we're talking about the ability to have distributed ACID transactions. Next slide, please. So let's get some context of what the YugabyteDB architecture kind of looks like. So here we have an example, a diagram. On the left side, we have our clients. Here we have microservers, but you can have a single client trying to connect to your database. And here, since we're talking about YCQL, the Cassandra compatible API, we're going to have the clients connect to that query layer. So we're going to connect to YCQL, and from there, the YCQL layer will connect to our distributed storage layer, which is our DocDB. So remember, the query layer for YugabyteDB supports both Cassandra API and the Postgres API. The Cassandra compatible API, the YCQL language or YCQL, has SQL-like queries and table structure for fast semi-relational row lookup. There's also the Postgres compatible API, which is also called YSQL, just for context. So YugabyteDB uses DocDB as its distributed document store to handle the automatic sharding while maintaining strongly consistent replication. So it's very critical for ACID compliant distributed transactions. So DocDB also implements a multi-version concurrency control for internal data consistency. Next slide, please. So here we're going to talk a little bit about the difference between your traditional SQL databases versus what YSQL brings to the table. So a lot of that conversation really centers around the differences between normalization versus denormalization. So in traditional relational databases, tables were normalized in order to reduce data redundancy and retain data integrity. Now, this meant that tables were structured to use foreign keys to connect or join to other tables to ensure there's only a single source of data. Although successful for a long time, normalization became limiting as workloads increased when applications began to scale with the internet. Complex queries that required multiple connections to tables caused large increases in network latency and disrupted the user experience. In an effort to avoid that network latency with the associated joins, Cassandra removed the joins and denormalized the table. Now, this resulted in much faster reads and writes at web scale. This also means that the data to satisfy a query must be located on a single table. So conversely, denormalization did increase data redundancy, and it made writes more expensive when we're talking about smaller workloads. Next slide, please. So let's compare a little bit about Cassandra and YCQL. So of course, here in order to achieve linear scalability, like I said previously, Cassandra sacrificed consistency and data integrity. YugabyteDB, however, was built with consistency in mind and achieves linear scalability with strongly consistent replication. So thereby retaining its data integrity. Although quite similar to CQL, which is Cassandra query layer, YCQL has undergone enhancements to retain ACID-compliant distributed transactions. Next slide, please. Here we'll be talking about the Cassandra query language compatibility. Number one, we're talking about the data definition language. You can see a lot of similarities there with Cassandra, if you're familiar with that. And you can see a lot of familiarity with relational SQL as well. So this is just a small sample of the language compatibility. Notice that many of the conditional operators, as well as the data definition and data manipulation language keywords, remain the same. By leveraging Cassandra's query language, Cassandra developers can be productive using YCQL and YugabyteDB on day one. So here we're going to go to the next slide and show key spaces. So here, when we talk about key spaces, so what is a key space exactly? Well, a key space is that topmost container that will be located inside your database cluster. And it's very similar to a database if you're not familiar with Cassandra. So the syntax to create and connect to a key space is very similar to the data definition with SQL. So create, of course, is the YCQL command that will create and name a key space. The use command will be used to connect to that key space, and then the drop key space will remove the key space from the cluster only if the key space does not contain any tables. In the next slide, we'll look at how key spaces reside inside that database cluster. So in order to achieve high availability and resiliency, YCQL replicates and distributes the table data across nodes in a cluster using its distributed document store, docdb. A key space is the top level container in a cluster that stores the tables. In this example, a request from the client is received by node 1. And in order to satisfy that request, a connection must be made to the key space in order to access the data in the tables. In the next slide, we'll see how to create a table. So here we'll see we're using the create table statement to create the table music. So the table music is created in the My Catalog workspace, in the key space, excuse me. Due to the semi-relational nature of YCQL, complex data types such as sets, lists, maps, and JSON-B can be used to define the data type of an attribute. This gives it that NoSQL semi-relational ability to have more complex data models. Note that the data types of the elements inside the set, list, or map must be defined. However, in JSON-B, it does not. So in the next slide, we'll talk a little bit more about the distributed document store. So here, once a table is created in YugabyteDB, the table data is then distributed amongst the nodes of the database cluster. So docdb automatically distributes the table data across the nodes in the cluster so that no single node becomes a bottleneck to high performance or availability. So in the next slide here, we can see, we'll talk a little bit more about the primary key in the next slide. Thank you. So here, just as in SQL, YCQL uses a primary key to uniquely identify each row in the table. In YCQL, a primary key must be assigned in every table definition. So a YCQL primary key consists of one or more partition keys, as well as 0 or more clustering keys. So the clustering key is not mandatory. However, a partition key is in order to have a primary key. So a partition key defines which rows of the data will be located in the tablet. So I think we dropped off our... So the clustering keys are used to provide uniqueness for the primary key. For a given tablet, the rows are ordered by the clustering keys in order to further enhance the query performance. So next, in the next slide here, thank you. In YCQL, shards are organized based on the values of the partition key. In this example, the artist attribute is defined as the partition key as identified in the inner parentheses. If there are no inner parentheses in a primary key definition, then the first attribute is identified as the partition key. The year and the song attributes are the clustering keys. So notice that the clustering keys order the rows in the shard. So the reason they do this is to really achieve those blazing fast queries at web scale, at really huge workloads, okay? So as you can see, by default, the order of these clustering keys is in ascending order. In the next slide, we'll talk about the sharding strategy. So in order to ensure that the nodes in the cluster have a balanced workload, YCQL uses a consistent hash strategy to distribute the shards in the cluster. With hash sharding, data is evenly distributed and randomly distributed amongst the shards using a sharding algorithm. This is the most efficient way to automatically distribute data evenly across the cluster for really large workloads. So in the next slide, we're going to give you the distinction. So in YCQL, shards are organized based on the values of the partition key. So in this example, the artist attribute is defined as the partition key. Here, instead of shards, as you can see, YugabyteDB actually uses the term for tablets. So those can be used synonymously or interchangeably in YugabyteDB. So going forward, we will be using the tablet terminology just for reference. So as in the next slide, as you can see, we have this tablet distribution across the nodes in our database cluster. So in this example, node 1 receives the request from the client, and if that query requests the artist value contained in tablet 1 as a part of its condition, then the query will be satisfied by accessing tablet 1. But if not, then the node locates where that tablet data is residing. So in the next slide, we'll talk more about the clustering keys. So remember, clustering keys were not mandatory to have in a primary key. So the clustering key is responsible for the data sorting within the tablet itself. So this approach allows for those really fast retrieval times. So by default, clustering keys, also known as clustering columns, are sorted by ascending order. But if you wish to modify that clustering order, you can use the with clause to modify the sort order, as I've done here in this example on the left. Notice that by modifying the sort order of the clustering keys, like in this example on the right for Beatles, we'll see that the most recent songs will be displayed first. Note that the order of the clustering keys, when defined in the primary key, will determine which attribute has the sorting priority. So as you can see here, year will be sorted first, and then song will be sorted after that because of where year came in the primary key definition. So in the next slide, we'll talk a little more about the DML, or how to modify a table with YCQL. So here we see the alter table. So in YCQL, the alter table statement is used to add a new column, or drop a column, or modify a column name, or change the property of a table. So a new column called tags is added to the table music. So in the next example, the column table has been dropped from the table. Next, the column year has been renamed to release date. So in the final example, data expiration property has been added to the music table. So that means that in 1,140 seconds, the data on that table will be deleted. Also, in order to remove data from the table, you may be familiar with the truncate table command. So you can just use that, truncate table. Now this is used often to remove data from a table, but actually the table definition or the table properties will remain. So we're talking about indexes and different other properties that you may have will actually be retained with that table definition and the table schema as well. However, the data only will be dropped. You can also use the drop table command in order to drop the table. So on the next slide, please. Thank you. We'll use the drop table command. and that will actually drop the table. Sorry, a little typo here. And that's the semicolon on the drop table that is necessary, just as FYI. So on the next slide, we're going to go to the next section. So I know we talked a little bit about data definition languages. We will talk more about the data manipulation languages as well. So on the next slide here, we'll talk about how Cassandra is different and how YCQL is different due to the fact that they are really focused, laser focused on the query-driven data model design methodology. So what am I talking about there? So in your traditional relational databases, a lot of the data model is actually driven by what the data looks like. So it's more of a data-driven model. So in a query-driven data model, you'll determine how the application will actually access and query the database. So by defining the application's queries first, you can really design the data model to satisfy these queries as efficiently as possible. So that's really the kit and caboodle, the big takeaway. If you take anything away from this presentation, it's that Cassandra YCQL defines their data model from how to satisfy the queries as efficiently as possible. So there's a lot of pre-planning for this type of optimization and performance gains. But in the long run, the workload, when it becomes really large, will attain that linear scalability. So here we're talking about the 4 stages of the methodology. So we're talking about the conceptual model. So really here, we're just really trying to collect all the objects that we really want to look at, especially all the, even though the relationships between the entities don't really matter as much, it's really good to know what that is because it'll inform the overall high-level view of what your data model really should look at the end of the day. Then we'll hone in on the data access pattern and really identify what the application's requirements are, what the application needs in order to satisfy its queries. And next, we'll talk about the physical data model and really define what the tables need to look like in order to satisfy these queries. And remember, we're trying to use that single table design. So each query will only hit a single table. And specifically, we not only want it to hit a single table, we want those queries actually to be satisfied by a single tablet. That way it won't have to deal with the added network latency that you might get in what you would consider a distributed document store. So next we'll talk also about the optimization and the tuning in order to improve the query performance using a query plan. So in the next slide, we'll really give an example of what we're going to be looking at and what we're going to actually use for our data modeling example. So here we're talking about e-commerce site. Here we have your basic e-commerce customer that wishes to create a wish list. And of course, on this wish list, we're going to have all these products. So really identify the 3 different entities. We have the user that can have many wish lists. And of course, the wish list can have many products in it. And of course, we have all the attributes around each of the entities. The user will have its name and its ID. The wish list will, of course, have the wish list ID, whether the wish list is public or not, and the wish list name. Then, of course, you can have all the information on the product. So obviously, as you can see, this example is really simplified in a real world enterprise case. Of course, there would be many more, much more complicated type of data model, but for this example, we decided to slim it down and give a simple example because there's definitely some key takeaways we'd like to deliver here. So on the next slide, we'll actually just hone in a little bit more on what the conceptual data model looks like between the user and the wish list and really look at that relationship. And of course, like I said, the relationship in a semi-relational or NoSQL, Cassandra, or YCQL data model is not that integral to creating the data model, but it just gives you a little context of how these entities need to relate to each other. So in the next slide, we're going to look at just the relationship a little bit more about how the wish list relates to the product. So of course, a wish list can contain many products. So the wish list ID, and like I said, the different attributes and how they are related to each other. So that was a conceptual data model. We defined all our objects and really defined our data domain to see exactly what our database needs to have inside of it in order to satisfy those queries. So really all this information is really going to reflect on what the queries need from the data model. Okay, so in the next slide, we're going to talk a little bit more about the data access pattern. So in this step, you'll determine how the application will access the database. So by defining the application's queries, you can design the data model to satisfy the queries as efficiently as possible. This pre-planning for optimization and performance of the queries will help in the long run when the workloads become much larger. So here we have an example of the data access patterns. So there's a couple of things happening here. So first off, the queries, of course, provide all that very important information that really formulates how the tables and the tablets, specifically the partition keys that really form those tablets, should be designed in order to satisfy that query. Other important considerations include identifying the workflows that contain really high frequency of use, or really we're talking about the business domain importance, the application, the mission critical workflows that must be satisfied. Also, it tells you which patterns contain primary versus secondary access points. So really we're talking about first point of access into the application or secondary after you've already connected. So it's crucial to prioritize these critical queries by creating tables to satisfy these queries and selecting the right partition keys that will define your tablets. So in the next slide, we're going to go to the next step, and we're going to talk a little bit more about the physical data model. So here, this is step 3. Okay, we're going to actually create and define the tables that will satisfy each query. So the physical data model really defines the tables by defining that partition key. So the next slide, we'll talk about the physical data model. Thank you. So note that the condition where the where clause is really establishes the partition key. Okay, so the where clause predicate, here we have example as user ID, really lets you know what your partition key is going to be in your table, because when you actually run this, you only want to connect to the tablet that has the necessary information that you need. And in this case, the user ID will inform or define that tablet and satisfy that query. So in the next slide, we'll talk about more about the table design. So in this diagram, a table is created that will satisfy the search for lists by user query. Note that the where clause predicate expression defines the partition key. Other attributes required by the query must also be included in the table so the query can return all the necessary data needed to satisfy that query. So note that the wish list name was selected as a clustering key here. In this case, if the user has multiple wish lists, the wish list will be returned in ascending alphabetical order, starting with A. Next slide, please. So here we're going to talk a little bit about primary key selection and so the primary key can have a single attribute, which is called the simple primary key. You can have multiple columns in that key, and you would call that a composite primary key. The attribute will become the partition key if there are no associated clustering keys. So the primary key can also have multiple partition keys and clustering keys, known as the composite primary key. The combination of these attributes must be able to uniquely identify each of these rows. In YCQL and Cassandra, selection of the partition key determines the data distribution of the cluster and its nodes because the partition keys define the size of each tablet. Therefore, improper selection of the key can result in inefficient operations of your database cluster. To select the correct attribute for a partition key, it's important to consider the following factors for the attribute. It's important to select a partition key with high cardinality and evenly weighted number of unique values. Of course, low mutability or something you don't really want to change that much. And it has to match the required data access patterns of the application, namely the query's where condition. So in the next slide, we'll talk a little bit more about how it's important to balance your workloads. Now, in this case, we talked about being able to select the correct partition key. So if you select a partition key that doesn't have a lot of unique values, let's say it only has, let's say you went to an example where one of the artists had 50% of all the values and all the other artists only had bits and pieces, then you would have an unbalanced workload. So the problem with that would be you could possibly have a hot partition, which means that most of the data would be located on one node because a really large tablet. So in order to do that, you would probably, to avoid that, you would probably add another column for your partition key to give you a composite partition key to avoid that. What that will do is break up that large partition into smaller partitions or tablets. So in the next slide, we'll talk about really the search wish list by product table design. So here we're designing the products by wish list table. So here, for the search for products in a query, the condition predicate will determine the partition key. So really quick, what is this? So this is the access pattern to actually look at the product catalog. So in this case, you would look at the product catalog in order to add products to your wish list, just to give you a little bit of context, okay? So here, in the result set, the query must contain the product name, price, description, as well as the name of the wish list. So in the next slide, we're going to talk about adding a product to a wish list from the product catalog, okay? So in this insert statement, you're not really searching for a particular record, you're not really filtering things, but just appending the record, right? So there isn't a particular need to search using an index. So in this case, since you're just adding a product to the wish list, you can actually use the same table we used previously, okay? Having less tables is good. It's a good thing. Having multiple sources of truth that need to be maintained and written to will actually raise the cost of the write. So really you want to reduce the number of tables as possible. So on the next slide, we're going to talk about searching for products by category. So this is a pretty basic access pattern. Let's say you're looking for party favors. Sorry, I have my daughter's birthday coming up. I'm looking for party favors online. So you look at party favor category and look at all the different products that you see. So a very common access pattern for e-commerce solutions. So when you search for products by category in that query, you really want to look for the catalog that will be searched by the category. So to satisfy the query efficiently, a table will be created to align with the partition key with the where clause predicate. So in this case, since the partition key will return many unique values, the cluster keys are really important because they really organize your result set coming from the category query. Next slide, please. So here we're going to actually talk about a similar, but not exactly the same type of query. So in this query, you're actually going to search the product catalog by name. So let's say I need batteries. I'm going to look for Duracell, and it's going to bring me back the Duracell battery from my product catalog. So just an example of what this access pattern looks like. It's a pretty common access pattern, and it does feel a little bit similar to the last access pattern we talked about when we searched for a product by category. So just to satisfy the search for product catalog by name query, the query statement was first designed to satisfy the access pattern. So in this query statement, the product name is used as the where predicate. Therefore, the table is defined with the same attribute, product name, as the partition key to ensure that queries use the primary key to search as efficiently as possible. Once again, we're talking about creating a tablet that will satisfy this particular query by using the product name predicate as our partition key in our primary key. So in the next slide, let's do a little quick overview of the tables that we looked at and some of the access patterns that they satisfy. So first and foremost, we're looking at the search wish list by user and defining the partition key in order to satisfy that query. And then of course we have the products on by wish list, and then adding a product to that wish list really maintain the same table. Then of course we have the search catalog, search the product catalog by category, excuse me. And then we also have, of course, searching product catalog by name. So as you can see, I just want to bring a lot of attention to the bottom two tables that are highlighted here. So as you can see, a lot of the attributes are actually the same. So you're looking at the schema and the definition, and you see a lot of redundancy here. So that means there's a lot of redundant information between these two tables. So in the next step, we're going to try and really optimize that data model in order to reduce the number of redundancies. And once again, just remember, the more tables means the more sources of data to maintain, which means to more costly writes. All right, so in the next slide, we're going to really talk about the optimization and the tuning of our data model. So after completing the first three steps of our data modeling methodology, we really have a nice rough draft of what our data model looks like. So however, to ensure that the data model really scale in a production environment, the queries must be tested for efficiency. So in order to make a data model more efficient, we can tune the data model to reduce the redundant data by lowering the number of tables, limiting primary table access, and limiting the number of rows that need to be scanned in order to satisfy a query. I just want to take a moment here and see if there's any discussion in the chat. So in the next slide here, we're going to talk about the data model optimizations that we can use. All right, so here we're going to consolidate the number of tables. So we can use the table products by category in order to satisfy the query products by name as shown in the highlighted statement. So can we do that? Can we instead just use this table and just query something else in the predicate? So in order to test this theory, we're going to use a tool called the query plan and discover if the queries are running efficiently. So here in the next slide, we're going to talk about the query plan and how we can use the explain keyword. So a query plan really helps us trace the sequence of the database operations necessary to really execute a query. So in this glimpse of the database internal operations, will help determine if a query will be inefficient or efficient, will be costly, or will it be slow. So this is a very important step because not only when creating a data model, but something that probably should be done pretty routinely whenever the data model changes. For instance, if you have feature additions or data access path modifications or any kind of like application workflow change. So the explain clause can help evaluate the different CRUD operations as you saw here. CRUD, I mean create, read, update, and delete operation. So you can actually just prepend your query with the explain keyword in order to get a report. So as you can see on the right side here, we have an example of the code. We have our explain prefix to our select statement. As you can see, we are getting back a sequential scan. SEQ stands short for sequential. And then here we also have the explain, a query plan for the write or the insert, where we append a product to the wish list. And you can see here we have a query plan, and it doesn't really tell you, there's no scan here. Like I said previously, it's not really searching for, it's just appending to a table, so there's not actually no scan needed, okay? So on the next slide, we're gonna talk a little bit more about the different scan types that we talked about. So we just gave an example of what a sequential scan looks like. And here is an example of some of the other scans that are possible shown on the left side here. So here you have your sequential scan. So what is a sequential scan? Basically, it scans every single row in the main table. So you have to access the primary table, or here we're talking about the main table here, and you have to scan every single row. So just imagine why we're using YCQL, why we're using Cassandra. It's because we're really implementing web scale solutions. We're talking about tables. When I say table here, we're not just talking about the small tables that I'm dealing with in this example, but we're talking about tables that have thousands and thousands of rows. Really, we're talking about these database clusters with hundreds and hundreds of nodes in them. So really, we're talking about web scale, huge petabytes of information, okay? So when we're saying scan every row, we're talking about an operation that will take a really long time and cause a ton of latency and really disrupt the user experience. So sequential scan needs to access the main table and read every row, but an index scan actually uses an index in order to find the matching addition. However, an index scan still needs to access the main table in order to retrieve that data, but you still have that primary table access that's needed. However, an index-only scan is the most efficient scan, since it doesn't need to access the main table. It can actually get all the data from the index itself. So a primary index scan uses the primary key in order to satisfy the query. So that primary key query is actually quite efficient. Note that the time complexity needed to scan a table with thousands of rows in the chart, as shown in the chart on the right. So as you can see there, as the rows of table really increase, these sequential scans rise almost exponentially in their time complexity. Some of you may think of big O in this circumstance. So really we have a really large big O in this circumstance. So the larger it gets, really we're having tons of latency, as opposed to the index-only scan, which is completely flat and linear. So this chart compares the time complexity between the sequential scan and the index-only scan. So obviously for our linear scalability model, we're really looking to try and achieve the index-only scan as much as possible. So in the next slide, we'll talk a little bit about the query plan demo. So notice that when the table products by category is queried using the attribute that is not the partition key, in this case it's product name, when actually this table's partition is actually the category, the query will need to scan every single row and gives us this sequential scan. So automatically we can see this is not going to give us that linear scalability that we want in YCQL. It's actually going to be, really slow when we're talking about web scale. So on the next slide, we're going to talk a little bit about indexes. I know we talked a little bit on the previous slide, so here I'll give you some context of what I'm talking about when I'm talking about indexes here. So an index it's actually a data structure, and it contains a subset of the attributes from the table. So along with a key to support query operations. So you can retrieve data from the index using a query in much the same way you can query with the table. So a primary index is automatically created when creating the primary key, since it's assigned to the table when created. A table can have multiple secondary indexes, which allow a table to be queried efficiently in multiple ways. So in YugabyteDB, secondary indexes are stored globally, which allows for a strong consistency of data. Definitely a big distinction with Cassandra. This is definitely a YCQL specific attribute, having that strongly consistent data replication. So on the next slide, we're going to talk about how indexes work in YCQL. So under the hood, secondary indexes are stored in global data structures that rely, on distributed transactions to replicate and distribute indexes across the cluster. So index tables are sharded and replicated across nodes, just like user tables. The two-phase commit for transactions ensures that the index is strongly consistent and remains fast. Next slide. Here we're going to talk about how to actually create an index in YCQL. So once again, we are using the Cassandra query language in order to use this to create this index. So we're using the create command. So here we're creating a secondary index to associate a specific index to associate the product name to this table. So by designating the name, by creating the product name as the index, we're going to really try and we're going to allow the query to have an index-only scan and give us that linear scalability. So by designating the name of the index is actually optional. However, the name of the table and the attribute must be designated in order to create the index. In order to enable secondary indexes for a table, transactions must be enabled. Very important here. So we can see at the bottom statement, with transactions enabled is true. Very important in order to enable indexes in YCQL. So on the next slide, we're going to talk about the include clause. So include clause is specifically used in the create index statement. So we can use it to add more data into the index in order to create that index only scan. So the purpose is to limit access to the main table by providing a covering index. Okay, so essentially it creates an index that's able to completely satisfy the query, give us the index only scan, and eliminate trips to the main table to retrieve that data. Here we use the description column in our covering index in this example. Next slide, please. Here we'll be talking about how to create a unique index. So a little bit different than what we used previously. Unique indexes are mostly used more for data integrity, data validation, data verification, just to try and really keep your data from getting corrupted. So a unique index is a type of index that assists in data validation and data integrity. By creating a unique secondary index, the key is disallowed from having duplicate values in the table. This is especially useful when you're trying to maintain data integrity for rows of data that must have unique values, such as product IDs, phone numbers, or emails. Next slide, please. Here we're going to talk about partial indexes. So a partial index is useful by limiting the number of rows that are scanned in order to satisfy a query. A use case would be to limit the search for a product only for locations in a very specific region. So here we're talking about indexes that are created on a subset of a table for more efficient queries. So here we're actually reducing the number of rows that need to be scanned in order to satisfy the query. So less rows that need to be queried, less rows that need to be scanned. Obviously, that's going to increase your performance. So here we're just limiting which warehouses will be added to the index. So maybe you're doing this because there's only a certain number of warehouses that are located in your region. So you want to keep that scan for products in your warehouse to be localized. And we can do this by creating this index that only contains warehouses that are located in your region. So therefore, you don't need to scan a warehouse somewhere in Australia when you live in an area and you're not going to be able to ship there anyway. So it's just reducing the amount of data in that table that needs to be scanned, okay? So in the next slide, we're going to talk more about the advanced data types. So this is specifically important in a semi-relational database like YCQL, because of course we're talking about being able to query all your data from a single table. So what helps is if you have the ability to have all your data in that single table, and these complex advanced data types really help you do that because it gives you access to things like lists. If you're familiar with arrays, it's just your ordered list. Then you have your set, also known as an object in other languages, which is your unordered list. And of course, your map, which is your key value pair. And then, of course, you also have your JSON-B, which is your sorted JSON. So here we have a few examples of how to actually use your, basically here are rights and how you actually data into these advanced data types. So on the top, we have a list and we have a number of warehouses that we're adding to our warehouse IDs. And then on the bottom, this is your JSON-B. And what's interesting about JSON-B is that there's a couple things that make it the best practice to use above lists, sets, and maps, because of the fact that JSON-B can actually allow you to use lists, to use sets, to use maps within its JSON data structure. And also, JSON-B is able to be queried, so you can actually query the keys in the JSON-B, and you can use that in your query predicate, in your where clause predicate, versus lists, sets, and maps, which really don't have that ability. So really JSON-B is the way to go since it has those enhanced attributes or properties there. So in the next slide, we're going to talk a little bit more about indexes that use these advanced queries. So here, once again, we're using SKU details, which is JSON-B data type. So we have created the index here on the products by ID table, and we're actually looking for the name for the SKU details. So on the bottom, we're actually going to do a read, and we're going to search for that index that we created for the JSON-B. So this is just an example of how powerful JSON-B can be in YSQL development and how it is a little bit superior over using the other advanced data types, such as lists, maps, and sets, because they don't have this ability. So just want to make sure. So in the bottom, we can see we're doing a read from the products by category table where the SKU details name is going to be searched for Bluescapes, okay? So in the next slide, what we're going to be looking at is really our time to live feature. So in YCQL, we have this feature called data expiration. So data expiration is really specific to Cassandra and YCQL, and it really automates the reduction or the removal of data that has been deprecated or doesn't really have that much meaning anymore. So automatic data expiration is really quite useful from a data model standpoint, since removing irrelevant or deprecated data will reduce operational costs, because guess what? That's one less thing that needs to be scanned or looked at. So time to live is a data expiration property that's used for data that is time sensitive or private. This feature is often used when dealing with time series data. So time series data, often referred to as time-stamped data, it's a sequence of data points indexed in time order. So time series data is data that's collected at different points in time. So some examples of time series data include IoT, temperature readings, health monitoring, cryptocurrency prices, real estate, and much, much more. So here in the next slide, we're going to talk about the different levels of data exploration and how it's scoped to different levels. So here, the data exploration is scoped to the table level. So the data deletion property, time to live, can be scoped to several different levels, such as tables, columns, or rows. So in this example for table level TTL, the table will be deleted with the default time to live property, which is set here at 10 seconds. So in the next slide, we're going to talk about the row level TTL. So when using in a row level TTL, or time to live, using TTL property can be set using the insert or update statement, excuse me. So this is how you implement it. You implement the row level TTL property by using insert or an update statement. So in this example here, the row containing these values and this property will expire in 10 seconds. Okay? So once again, you can either use update, you can also use insert as well in order to set this property. And then 10 seconds later, all the data in that row will be deleted. So let's say you had a wish list for Christmas. Christmas has passed. You can actually set your TTL for the day after Christmas to erase that list, because that list maybe isn't that important to you, because next Christmas you'll have a brand new list. So this is a way to use the row level data expiration. Here we're talking about a column level TTL. So special note, when using the column level TTL, this can only be set with the update statement. It's a little bit different than the other ones. So rather than drop the column, the values in the column will actually be returned as one column. So it actually doesn't drop the column itself. It actually truncates or deletes the data or the values that are in that column. Okay, so remember so the expired data for the column is stored as a part of the docdb values and only works again with update. So next step, we're going to talk about, once we've completed this course, just to let you know, everyone is available to take the exam courses. So we do have a YCQL Development Fundamentals exam that you will be automatically enrolled in, as well as the YugabyteDB Intermediate exam that you will also be enrolled in. So you will get automatically enrolled into these exams. And then if you pass, I believe 80% of if you are able to get 80% of the questions correct, we will actually email you certification that you actually completed the fundamentals and the intermediate course. So you can ask, and why do I get two? This course that we talked about today did combine two of the courses together. So if you have a question of why you get two certifications, it's because as a bonus for DSS, you were able to get a combined course for today. So that's why you get that automatic enrollment in both of these exam courses. So real quick, there is a example, or a, shall we say, a set of hands-on demonstrations I would like to show you, but unfortunately, I'm going to see if possibly Seth can look at, oops. So I'm going to go ahead and send this over to you, Seth. So maybe you can help me show an example of our hands-on demonstration for today. So hopefully, Seth, you can take a look at that and release our Git pod. So this is basically yes. Okay, so I will be sending you an example of our repo. And in this repo, since we do have some technical complications of today, I really do apologize for that, but just wanted to give all the participants here a hands-on lab where they can take a look and see how to.
Hey, Mark, can you hear me?
Yeah, yes?
Does this repo work?
Yes.
Meaning if it will start up in Gitpod?
Yes, you will have to start it up in Gitpod. The repo. So what we're sending you now is the hands-on demo lab that I had created. And here, what we're actually using is a Docker container called Gitpod. Basically, what Gitpod will do will give us an environment that actually has YugabyteDB already installed, and it'll actually deploy a 3-node cluster for us. So right now what's happening is that repo is being deployed into a Docker container in Gitpod. And once that container has been successfully provisioned, obviously currently it's composing the image. We created a custom image that actually contains YugabyteDB. As you can see here, once the Gitpod container is starting to render, you will automatically see that the cluster has been created. So now we're just waiting for the cluster to be deployed. And as you can see, if you look at the lab here, you can see that. So we do this in order to give everyone a hands-on experience with the DB cluster. As you can see there, the cluster has been successfully deployed. And so you can actually go to the top lab there, not that one, but the other one, not the green one, on the left side in the File Explorer, in the Folder Explorer. You can go to the 01 YCQL Intermediate on the left side. Yeah, there it is. Very good. So here you can actually see that here, this is called a Jupyter Notebook. As you can see there, we do have all our 3 nodes deployed. And here, there's some basic setup steps. This is an IPython experience, but it gives you the ability to look at code and run these cells. So the very first cell, what we're doing is just assigning environmental variables. Not that exciting. We're just giving file paths. And we're just showing telling the system where our data files are located in our sequence file. So as you can see, everything's been stored. So if you go, you can show the actual variables here that have been located. So as you can see there, we have our data files. We have letting the cluster know exactly what the IP addresses are for the 3 different nodes. And then in the next cell, as you can see there, what we're doing is we're actually creating a key space. And the name of this key space that we're going to execute here is called DB_YBU. So we'll be creating that database there using the YCQL shell. So this is an API that we're using, this command line interface to connect to the database. And as you can see here, we described the table. So describe is going to be a YSQL shell command. And as you can see, the DB YBU key space was successfully created. However, there are no relations in that table. Here we can actually see there are system key spaces as well. And of course the DBYB, which is the user key space that we just created. And of course there's no tables currently inside of it, but we're going to go ahead and fix that real quick by going to the next cell. And in the next cell, we're going to actually load the DDL and the data from our file. So on the left in the Explorer there, we can see that we have our SQL files. And as we execute there, we can actually see, yep, on the files there, we can actually see we have our wish list DDL as well as our wish list DML. So these are the two files that we're going to be executing there. And then obviously we're going to be creating I believe it was all 3 tables. So there are actually 3 tables that are created. The last one might be truncated, but here we can actually see that the 3 tables were created successfully, and not only created, but we actually inserted the data as well. And the 7 rows are not showing, but believe me, there is another table there. So in the next step, we're just going to talk about the query plans, and we're going to execute some of these commands here. Just as an example, I know we're getting short on time, so we might not be able to get through all these examples, but here is the explain the query plan we're using for the read. So we're trying to read all the rows in the products by category table. As you can see there, by doing a select star, obviously we're doing a sequential scan. Obviously we're trying to retrieve in our result set every single row in the table. So clearly it's a sequential scan since we are needing to read every single row in that table. Okay. So in the next cell, we can show you what we're talking about as far as secondary indexes. We can show you different examples as well, if you like. Sure. Let's go to the next example here. And this is going to give you a sequential scan for a different table. So this table is the products by category. But here, what we're doing differently is we're actually using a condition for the product name. And what's interesting here, once we run this, it'll show you that we actually still ran a sequential scan, even though we are only trying to look for a specific row in that table. So again, sequential scan, not something that we really want, not going to give us linear scalability. It's something that we're actually trying to avoid. So in this next scan here, we're going to be looking at the where clause. And once again, we're going to show you that we used product name as part of the sequential scan. Okay. And once again, we got sequential scan once again. Again, we're using select star. And then here, we're going to show you this is a range scan that was completed, an aggregate scan, since we're using the sum function in order to get the quantity of the subtotal for our wish list. So that just gives you an idea of a different type of query plan that can be returned. Next, we're going to talk a little bit more about secondary indexes. So here we're going to use, once again, we're using bash commands, and we're going to connect to the YCQL shell API. So here we're going to go ahead and create an index for the key here. Hold on one sec. All right, as we can see here, we did indeed create. Yes, let's go ahead and execute that. As you can see, yes, that was a successful creation there. Hold on one sec. Okay, very good. Sorry about that. All right, so here we're going to talk a little bit more about trying to see what it looks like now that we created that index. As you can see, we describe the table, and when you describe the table, it clearly shows you what the indexes look like since the indexes are connected to that table, and it shows you what the index name is, and obviously it tells you what table that index is connected to, as well as the clustering order. And of course, transactions must be enabled as true in order for you to create secondary indexes in YCQL. Very good. So here, as you can see in our hands-on lab, in our next statement, we're going to try and look at the query plan, and it shows you that we actually did an index scan using that index. Very good. So here we can show you obviously the conditions for the query is going to be product name. So in the next statement here, what we're trying to do is show you a query plan. And here, the difference is an index only. So this is really the type of scan that we're really trying to get to. The reason why we got an index only scan in this case is because we selected the product name when we created the index there. Very good. All right. So in the next statement here, we're going to do is look at unique indexes. Really, once again, what are unique indexes? This is to help us figure out exactly how to get some data validation. So we're going to go ahead and execute that, create that index only scan. You might need to comment those other 2 lines, just so you know. Yeah, there you go. You probably need to comment that one and the include as well. Excellent. Now we're going to go ahead and describe the table. And of course, by describing the table, we're just validating that the unique index was actually created on the table. And as you can see there, we're creating the unique index on the product ID. Very good. Excellent. So just a couple hands-on steps. You can actually use this lab on your own. GitPod is a free service. So in case you want to get some hands-on experience on your own, we provide this for our learners today in order for you to see what it looks like to execute some of these plans. So here we have a range scan being created on our table products by category. And once again, we're using the condition for office supplies in our category and using the filter. And the filter is what makes it a range scan. So we're looking at prices that are above $30, okay? So this gives you the range of, okay, we're only looking at office supplies that are above $30. So that is the range. So by limiting what you're looking at, we'll speed up the query. So here we're looking at query plan for partial indexes. So just another example. All right. Very good. I think those 2 cells must have been combined somehow, it looks like. So here we're going to create an index scan. All right. Here we're going to describe the products by category table. And here, as you can see, we have our index table. Our indexes have been created. As you can see, there are multiple indexes on this table. That's something that you need to do in a semi-relational database because we don't have other tables to join to. So in fact, what we do is we create a very large table and we add lots of different indexes to this table in order for it to satisfy as many queries with an index-only scan as possible. So just to let you know that you can add multiple indexes to really increase the utilization of this table to satisfy as many queries as possible. So here we're going to show you the different ways of creating an index, and you can always change the clustering order of your index as well. Once again, this is to increase your speed of your query execution. So in our next example here, we're going to go ahead and take a look at the query plan for the read. So it looks like one of the lines looks like it wasn't commented correctly underneath that comment, it looks like. Yeah. Okay. It doesn't have a semicolon possibly at the end of it. Yeah. Okay. So here we have a range scan. Once again, range scan. This is similar as what we did before. We're looking at the category for office supplies, and it's only returning the price above 30 for those ranges. Okay. Very good. So those are partial indexes. The reason why you create partial indexes is to really reduce the amount of data that you're looking for in a table. So you're only looking for a specific range of data. By looking only at a specific range of data, you are limiting how many rows that you're looking at. And by limiting the number of rows you're looking at, you're going to speed up your query execution speed. When you do an analysis of the time, how long it takes you to satisfy that query, partial indexes really enhance that ability and really allow you to give you that linear scalability. Very good. Okay, so if we roll to the next cell, I believe that index will not be created again. So I think that once that index has been created, the error there is that the index is already created. It won't let you create that same index again. So here we're going to look at a couple different ways to alter the table. So there we added the warehouse IDs. And here we're going to go ahead and just describe the table. And we can actually see that the warehouse IDs that we created is there. And we created a list. Once again, it's an ordered list. And here we define the elements of that list to be text data type. So here we're going to go ahead and go to the next. There we go. Very good. So in the next statement here, we're going to actually add a tags data type. A tags column, which is a set data type. And in that set, as we can see there, all the elements in that set were defined as being a text data type. Then here we're actually going to be creating a frozen list. So here when we're creating a frozen list, basically that tells you that you cannot actually modify the list. As you can see there, store locations was created as frozen. So that frozen keyword lets you know that you cannot go into that list and alter the elements within that list. You can replace the entire list and you could drop the entire list, but you can't actually modify the list in itself. Once again, this is more for data integrity and really gives you a way to protect your data in case you don't want it to be modified accidentally. So here in this next cell, what we're going to do is we're actually going to create a JSON-B index. So once again, as I said before, we're going to create an index SKU details name. And we're going to actually, as we did in the slideshow, we're going to actually create a JSON-B index using SKU details. As you can see here, we're going to actually go ahead and describe that table. And by describing the table, we can actually identify and just validate that our SKU details index has been created there. And as you can see, it's using the name key inside the JSON-B SKU details in order to efficiently query the database using the JSON-B, specifically for the name key. So very good there. So then, of course, if we test whether that index is working properly, we can actually use a query plan, and it shows us we actually are able to create an index-only scan using that key condition. Once again, SKU details as the name of the key. Okay. So very different than some of the other complex data types. The extra flexibility and usability of JSON-B is quite important. And then here for our very last demo of the day, we're going to go ahead and use the time to live. And we're just going to give a couple examples of how to use that. Here we're using the table to-do list by user. We're going to go ahead and execute that. So we created the table to-do list by user. And here we're actually going to, all right. So we probably need to actually comment out lines 7, 8, and 9, or probably just keep them on the same table. There you go. And so here, once we have actually created that table, we're actually going to use line 7 to actually insert data into that table. So once again, it's important to see that what are very good. And then we can actually select and see if our data, as you can see, it's been over 5 seconds. So that insert has already been deleted. So yeah, we can just run it again and show you. There you go. There's the row of data, but when 5 seconds is up, it's going to go ahead and delete itself. So it just gives you an idea of a row level, a row scoped time to live data expiration example. Okay, very good. All right. Excellent. So here, there you go. So we have our table of data, and then just a few seconds later, yes, it persists for at least 15 seconds. And then 15 seconds is up, the data actually does disappear. So yes, gives us an idea of exactly how long it takes. So that is our presentation for today.